Good evening. As we assemble here today, consuming probably thousands of watts of electricity in this hall, we are aware of the fact that energy crisis is probably one of the biggest challenges faced by mankind at large. We have often asked ourselves if there is an alternative to powerless existence in the future. Is there a substitute for fossils? The Energy Forum Department of Management Studies and the EML team is proud to present Colonel Peter Gerritsen, a distinguished guest today, who will try answer some of these questions this evening and provide us with insights into a potential solution to the ever-worsening energy crisis. I request Nimit Jain, the Student General Secretary, to escort him to the dais and present him the bouquet. Sir, I invite you on stage. A former Service Academy Research Associate to Los Alamos, Colonel Peter Gerritsen is an air power and space power strategist in the U.S. Defense. He holds leadership positions in the Space Frontier Foundation, Space Development Steering Committee, National Space Society, and is a recent honorary member of Sigma, a think tank of science fiction authors. A recipient of the U.S. National Space Society's 2008 Space Pioneer Award, he is currently a visiting fellow at the Indian Institute for Defense Studies and Analysis, New Delhi. Put your hands together for Colonel Peter Gerritsen, whom I invite for the much anticipated lecture.
Can everyone hear me okay? Yes? Before I start, I just want to say, I consider it a tremendous privilege to be here and able to address the young minds who are really building India and the world. And if there is likely to be a long-term solution to the problems I'm going to bring out, it's probably going to be you. If you look within my own country, the largest number of students from abroad doing math and science engineering come from India. And as I have worked through our R&D level throughout the entire United States, the presence of persons of Indian origin is vast. They're among the best. They're among the most creative thinkers. So I feel very privileged to be able to talk to you and hopefully ignite your minds, and also very privileged to be able to speak to your faculty who are molding and encouraging that. This is a little bit about my particular project. I am a visiting fellow, taking a year sabbatical from my typical work, which was I was a strategic planner at the Pentagon, looking 30 to 50 years out at the long-term type of problems that we would face as humanity, and trying to think of solutions, both technical and relational, to ensure that the world would stay a stable and good place and you could see development and people move out of poverty. I was very lucky that at the conclusion of my study on space solar power for the Department of Defense, that during that course of that study, I became aware of work done here in India. And I was very fortunate that about that time, when it was time for me to change jobs, a fellowship opportunity came up from the Council on Foreign Relations, and that the Air Force was willing to let me go on a sabbatical. And that through a series of consecutive miracles, I was able to find an institution that was willing to host me. I was able to get permission from your MOD, from your MEA. The Air Force would release me, found a place to stay, all of that. So I have 1 year to try to do as much as I can to catalyze this concept and to understand how we might construct an Indo-US partnership in order to move forward on an idea that I personally think its time has come. But I encourage you to look at not just the solution I'm talking about, but the underlying problem, because there isn't just one solution set. There are many. And I apologize if I'm having a bit of trouble with my throat. The air in Hyderabad, where I came from, didn't agree with me. All right, so the first thing I have to say is that this is solely my opinion. It's not the opinion of any of my host institutions, the IDSA, the Council on Foreign Relations, any US government agency, the government of India, or space advocacy institutions yet in our civil society. So I want to start with a little bit about your own situation here that I think is important to sort of cage and bring home things that matter. So there's a terrific book. You probably can't see it. It's Václav Smil, Energy in World History. And what he says is that no society that averages less than about 100 kilograms of oil equivalent per capita can provide even the basic necessities to all of its inhabitants. And that as you approach the equivalent of 1 ton, you start to see incomes rise, the quality of life noticeably improves, and that widespread affluence really doesn't happen until you're at about 2 tons a barrel of oil equivalent. The gold standard of developed economies that produce the highest amount of economic activity per unit energy spent is this 30 barrel of oil equivalent in Japan and South Korea. There are many countries that, of course, spend much more than that on per capita basis, but they aren't as economically productive. South Asia right now as a whole sits right here at 300 kilograms, and of course India is doing a bit better than that. So here is kind of that expressed in chart form. So you can see, that basically, with the exception of Bangladesh, that's right on the cusp of that problem, you're into the basic necessities for all. If you can push your per capita higher, you can see that noticeable improvement, and then widespread affluence comes about here. So getting there is, of course, a difficult problem, and I'll show you another couple charts. So this is what's projected for you, going out to 2050 on the left and to 2090 on the right. So if you see, you're right about here at about 1.2 billion people, and by 2050, you will have increased your population another about 300,000 people to 1,500. And then, at the same time, your urban population is growing and your rural population is decreasing. And that's important because it puts significant limits on how far the small is beautiful philosophy goes. Because even though ground solar has immense potential, and you can't not do ground solar, what you have to realize is that if I have the same square kilometer of area in a rural area, it's supporting far fewer people. But if I put people in a skyscraper, the roof size is the same, but the number of people in it and their energy needs are much higher. So you have to consider what is the real available energy density. Then here's another, this is the outlook right now for how your energy growth is going to happen. And I'll talk a little bit more about this in the next slide. But I want you to notice that right now you're still forecast to have about 49% of your oil way out in 49% of your total generation capacity in 2090 as coal. And as you probably know, there are huge climatic problems, environmental problems with that. But I'm going to show you one more problem that's worth thinking about. Even with the expansion in nuclear, and take a look at how tiny the planned expansion in solar is. All right, at the present, India generates about 121 gigawatts of electrical energy, of which 56% or about 67 gigawatts is from coal. Your reserve production at the current rates, if you compare reserves to production, you have 212 years of coal left. To sustain your projected GDP growth, you're planned to increase your generating capacity 11-fold to 1,350 gigawatts by 2050, 44 years from now. That's in your 11th plan. That's an annual growth rate of 5.5%, which is not at all unrealistic and what you guys have been seeing so far. In fact, you peaked at about 7%. By 2050, you're forecast to be 49% coal. This is from your DAE study. But under the above assumptions, if you really calculate a 5.5% growth, you're going to exhaust your coal reserves a mere 13 years later. So think about, and I say that's a problem because think about the problem that you're building for yourself right now. Right about here, everything beyond this is gone. 50% of your generating capacity, 50% of your energy, gone. And don't think that you're going to be able to find that energy anywhere else in the world because they've got the same problem. China's growth and their long-term outlook for coal, and the United States, the other major, are going to have the same problem. The other thing you have to keep in mind is, as the transportation fuels peak out on oil, which is going to happen sooner, you're going to have to convert more of your coal to transportation and not just generating capacity. So worldwide, it's going to cause a significant problem. All right, now I want to get a little bit more into the positive side. So it's very, very easy to get depressed about the long-term energy situation. And what I hope today is to infect you with the idea that maybe it doesn't have to be that way. Maybe there really are long-term, truly green solutions that will catapult and create new wealth in the long run. It's very easy to dismiss an idea like the one I'm going to present because right now today we're pretty far from the reality of being able to put it together. But I want to remind you that this gentleman was the Federal Communication Commission commissioner, theoretically one of the most knowledgeable individuals on telecommunications in the world at the time he made this statement. In 1961, he said, "There's practically no chance communications space satellites will be used to provide better telephone, telegraph, television, or radio service inside the United States." And 4 years later, we launched it and it went into service. So this just shows you how misguided expertise can be and how a tremendously powerful people who have a passion to make it work can be. You can't see, unfortunately, PowerPoint changes from computer to computer. But this is Marshall McLuhan. He says, "Only puny secrets need protection. The really big discoveries are protected by public incredulity," meaning that we just can't believe that something could be possible. All right, I want to tip my hat here to your founder of your Department of Space in Israel, Dr. Vikram Sarabhai. This is a fairly famous quote for him, and what I want to call your attention to here is this. We don't have the fantasy of competing with the advanced nations in the exploration of the moon or planets or manned flight, but we are convinced if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. And what I will tell you is energy security and climate change are real problems, and real problems that space can deliver on. And I think you'll agree, having seen my presentation, that it's a far, far more ambitious space agenda than the one that's being contemplated by any nation today. So now I'm going to get into the actual core of my presentation, drilling up. So why do I think space solar power is the biggest idea in space and energy? Well, as you'll see, there's a problem with traditional renewables. If you add up how much you really need, it just doesn't add up. So the market for renewable energy and the market for aerospace, well, the market for renewables and for energy in general is measured in the trillions today. For aerospace, it's measured in the billions of dollar market. But if you could build these things, it would mean that aerospace was $1 trillion market, and it would mean that you would have a sustainable income source for a very, very long time. The other thing is it's very renewable. In fact, as I have tried very hard to sort through the competing claims of all the different types of possible renewable energy sources, I have come away that this concept is in fact the most benign, the most environmentally benign, the most scalable. That's the other problem, right? This is sustainable. The sun's going to be there and our friend for a good billion years before it expands to fry off our oceans. Of course, it'd be nice to have a plan of what to do by that time. But unlike even advanced nuclear energy, which is perhaps thousands of years of fuel before that's gone too, this energy source is going to be there for at least 1 billion years. And it is completely scalable. Even if you calculate the needs of the world at the end of the 21st century, after everyone has transitioned to a first world energy lifestyle, there's still enough up there to provide the energy we need on Earth. So let me talk a little bit about demand. Above you see a satellite image taken that shows the lights of the world at night, that gives a good example of what is and is not electrified. Below it is a plot of the high population density in the world, and what I would call your attention to is that they don't match. That there are huge swaths of area up here that are extremely population dense within your own country and close neighbors that are dark. Within your close neighbor of China that are relatively dark. Within your Indian Ocean region that are dark, and other places. That's energy poverty. That means that those people who live in those environments will probably never have the kind of opportunities and lifestyle that even we enjoy. It would be nice not to have to say no to those people, not to have to say, you know what, development can only go so far. Can't let any of you guys come up in the world because that's too much carbon, or there's not enough coal, or not enough energy. I think that would be a tragedy. To me, the great humanitarian crisis and question of our time is how do we find the energy to lift another 2 billion people out of poverty, to ensure that they can live the kind of life where they can self-actualize, and where we don't see a problem where in mid-2030s to something, we see a collapse in fossil fuel regimes. Everybody goes scrambling and goes to war because I got to get mine. And you can't have yours because there's only enough for me. So here's the outlook of how we're looking in the long-term demographic trends. The world is going to add another 2 billion people just by 2025. So that means that, let's see, if there's 6 billion now, that you could look around and this auditorium would be significantly more full than it is right now. And if you look at where the growth is projected, it's projected we're going to double our energy needs by 2025. And most of that is in the developing world, in India and China. So we have to think very seriously about where that energy is going to come from and make sure that there's a steady supply, and so that there's nothing to interrupt what is the dream of so many. Then there's this linked problem of climate change. This is looking back at the pre-industrial level of carbon dioxide in the air. Once industrialization took off, it skyrocketed. Now, to give you a sense of the scale of what's required to fix this problem, if I wanted to cap this at 4 times its pre-industrial level, 4 times, I would need to add 16 terawatts of carbon neutral energy. That's as much as the entire world uses today by 2100. If I said, 4 times isn't good enough for a stable climate, I need to come down to 2 times pre-industrial levels, I need 40 terawatts. 40 terawatts. I use 15 today. That's a scale problem. Now, here's the other problem that we all have to be vigilant about. And when I was with Air Commodore Gopalaswamy, and he was presenting last night, he said something that I thought was very important. He says, I talk about this problem and nobody's bothered by it. All of you should be deeply, deeply, deeply bothered by this chart. It keeps me up at night thinking about how we're going to solve this problem. This is the projected demand. Well, there are many sources, but this is essentially a picture that tells it well. This is the projected demand as the world adds population and as the world increases its per capita usage of total energy. Now, the wonderful thing about energy wealth is that when you're wealthy in energy, you end up having a good lifestyle, so you spend more time educating your children, a larger investment, so you end up having fewer children, so the population levels off. So at some point, you don't have to worry about whether or not you're going to be able to feed everybody. You don't worry about constantly being in poverty. You have a place. And that happens naturally with energy wealth. It doesn't happen naturally any other way. And I don't think most of us in this room are interested in draconian procedures where you limit who can and can't have children. So here is the outlook of fossil fuels plotted with time to 2100. Crude oil is going to be the first to peak in supply. It's not running out. That's going to be the crisis. It's the peak. Because when the demand curve keeps going up and the supply curve can't keep up as it always has, that's when bad things happen. That's when prices go up. That's when development slows. That's when poor countries are not able to put the energy they need into their own crops, and so their states fail. They become havens for unrest and terrorism. And that's when, as it gets so expensive and it cuts to the bone on what you need to make sure your hospitals run, to make sure your roads run, that's when big countries eventually come to blows and say, someone's going to get it, and it's going to be me. So this is a huge problem. Notice that even if you add the heavy oil, it only delays it a little bit. Natural gas, same thing, about 10 years later it peaks, and the same thing. Coal lasts for a while, but keep in mind that it's this total peak that you have to worry about. So what's going to take over after this peak? It's going to be renewable energy and nuclear. But guess what? You saw the previous slide I showed you. We're not on a pathway to replace that, are we? We're not. There is no planned expansion out here for massive increase in solar and wind. Even for nuclear, it's fairly modest. So, not planning is planning to fail. This is sort of the breakdown right now of our total energy breakdown. About 7/8 of our total comes from fossil fuels. About 1/8 comes from all of it, nuclear, biomass, hydro together. And of that, you can see, there's the breakdown of true renewables. So here's the problem, right? If we're looking to 2025, and of course we've talked about farther out to 2050, but if you look at the total resources in the world that people have estimated are there for renewable energy, it's really kind of a sad picture. You realize that biomass can only make so much of a contribution. Hydroelectric, when you really look at what's technically feasible, geothermal, wind, that leaves the big one, solar. Theoretically, there's practically some 600 terawatts, which is, in theory, way more than you need. But when you really look at how you would implement that, the picture is nowhere near as rosy. And there's a paper by Mike Sneed here, The End of Easy Energy and What to Do About It, that I highly recommend you Google. There are actually two charts that look almost the same. This is sustainable fuels. There's another one for generation that looks almost the same. But he went through and looked at what the advocates were saying. How much can I upscale it if I go max afterburner on all of them? You still come up with about a 62% deficit of what you need in 2100. We got to get creative. We've got to figure out how we're going to solve that problem, or it's going to be a civilizational crisis. So when you look at future energy options, what you'd like to have is keep in mind that our first energy transition was from wood to coal. In fact, much of Europe and the United States was deforested because there was such a demand on wood for making steel, iron, boats, various other things that were very energy intensive, that it drove us to the use of coal. And then eventually, around World War II-ish, we started going with oil. But that's not going to last. So we have to think about what the fourth energy transition is going to be. And so this is the standard that you should be setting for yourself. And unfortunately, it's not the standard that most of our planning departments and our governments have set for ourselves. It needs to be non-depletable. It's got to be environmentally clean. It needs to be continuously available. We can't really expect to have the kind of modern society we have today where we don't know if the power is going to come on or not be on when we need it. It's got to be in a usable form to permit efficient consumption and minimal infrastructure. And electricity is by far the most usable, most valuable source of energy. The electrical intensity is going up even as the overall energy intensity is going down. Now, I am not, please don't misinterpret, I am not advocating this idea as a total solution. You need to have a very, very balanced approach with a number of different investments. But when you look through what meets this ideal criteria, there just aren't that many options, and the few that are come pretty close, there's just not enough of them to scale up to the level of the problem that we anticipate. Now let me talk about supply. So that's where most of the world's energy comes from, whether it's wind or biomass or anything else. It puts out this unbelievably large number. Right now, we only need 15 terawatts. Soon we're going to need 30. Probably at the end of the energy transition, when everyone is lifted out of energy poverty, we'll need about 55. So here's what happens, though. It puts out this gobs of energy. About 120,000 terawatts strike the Earth's surface. Right there where it's striking out in space, the strength of the sun per unit area is 1366 watts per meter squared. Now, when we look at exploiting it on the ground, you have to realize that at the best place, near the equator, at high noon, I get about 1,000 watts per meter squared. No dust, beautiful day. But the problem is that the other side is zero. That solar cell puts out nothing. In fact, it only really produces useful energy for about 6 hours a day. It's about a 22% duty cycle. Now, when I take into account the seasons, that reduces significantly the power that I have in winter particularly, but averaged over the year. And then once I take into consideration weather, that number up there is about an order of magnitude smaller, depending on where you're at. So space-based solar is an idea to innovate ourselves out of this problem and to go after energy that's there all the time, not just at night, and energy that has higher amount per unit of used land. And it seeks to break this tyranny of the day-night cycle, not through distribution or through storage. It seeks to do it by changing the location of the collector. To give you an idea of how much energy is out there, how large this resource is, why it's worth thinking about going where the energy resource is huge and constant. Imagine in your mind that we were to go up to this, or this is obviously not to scale, but imagine that you were to go up to the ring where we have our geostationary communication satellites. And let's say that I made it 1 kilometer wide, not for any engineering reason, just to allow the scaling of this number here. And I said, how much energy passes through this that I might be able to mine? The answer is that there's about 212 terawatt years flowing through that every year. Now, what's important to realize is how big is that number? What does that mean? Well, if I convert all the remaining oil in the ground, all of it, it's about 250 terawatt years. So just ballpark, there is more energy passing through this ring than everything I got left in the ground that I'm depending on. And this is coming every year. That's income. This is my trust fund that I'm spending till I'm broke. So looking at it graphically another way, here's my 250 terawatt years. This is my annual oil production. This is how much I need in total energy. You can imagine that it's only a matter of time till this gets all eaten away. But even when I'm thinking about in the 50 to 55 terawatt range here, there's plenty up there, plenty that I can mine. In fact, and again, I encourage all of you, don't take any words or numbers I use from, figure it out on your own. But previous calculations say that you could put about 17,710 gigawatt satellites, so that's 177 terawatts. 177 versus 55, if we take it at the upper end. So now let me talk about the opportunity. When I was conducting the study for DoD and I came across this idea that was languishing, that almost nothing was happening with it, about the time that I was getting ready to put it to press, Dr. Kalam, your former president, an amazing visionary, made a speech at Boston University, and he's published other things here, where he says, what better vision can there be for the future of space exploration than participating in a global mission for the perennial supply of renewable energy from space? He went on to say how useful it might be, particularly for large-scale drinking water. And I was captured by that. I said, wow, here I am, some nobody lieutenant colonel in the Pentagon, thinking this is a great idea, publishing a report on it. India is talking about it at the level of their president. Wow. I need to go there. That's where the action is. And then, another little, and believe you me, I took notice of that because I also see this as absolutely strategic. I think that the nations that, that exploit this, they're going to be the dominant forces in the future world. I mean, think about how significant the scale and the wealth of this is. 55 terawatts added to the Earth's supply, green energy, would more than an order of magnitude, more than 10 times increase the global world product, the GWP. That's how significant we're talking. Then your own Aeronautical Society of India and the Astronautical Society of India came out with this document, recommendations in their 2007, that they wanted to generate a national consensus for a global space, aerospace and energy initiative. And the other thing that I want to say, and really I want to say it more for your teachers today, but also for you guys in the future. Vision is paramount. Vision attracts talent, it attracts capital. The reason why you have me here working for India is because of these visionaries that drew me here, because they had a vision, a positive vision of the future. So this was my report. You can find it online. It was a remarkable report, the first ever report done by the Department of Defense that was done open in the internet, completely released. You can Google it, NSS Space Solar Power. There's a lot in it, but bottom line was that it merits significant further attention from both government and the private sector. And we have seen a significant interest in private sector, but the reason that you can expect that it's not going to take off is that the capital, the buy-in costs are very significant, and there needs to be significant technology work in reduction, things that you probably excel at here. Once we came out with that, we were amazed at how many groups came forward to support what we had to say. And I'll just to give you a sense that it's also catching on in the United States, the National Space Society, which is actually an international body, and you actually have two, this is a civil space group that promotes a spacefaring civilization in general. You actually have two chapters here in India. One is in Pune, and the other is in Kolkata. And I would be delighted if I found out 6 months or now that there was one here as well. But they thought that it was one of the most important long-term solutions to meet those future needs. The AIAA, which is our technical society, same thing, possibly competitive with providing non-depletable source. The Space Frontier Foundation, another space advocacy group, could be an environmentally friendly, ecological, energy-producing technology. And then more recently, unfortunately, under the Bush administration, the idea was seen, one, as perhaps crazy, and two, as, unfortunately, a competitor with the existing vision. And so it was unfriendly to the idea. But it looks like the new administration, they've put up a web page under their Department of Commerce that at least is discussing it, which is highly encouraging. And the other encouraging thing is that as Obama, before he actually took office and had this change.gov website where he was interacting, one of the first 10 white papers solicited for public input was this space solar power solution for energy independence and climate change. And it was not written by the administration, but they thought it interesting enough to publish it. And they were saying that, hey, look, you know, fusion is much farther out than this idea is. We at least know how to make photovoltaic arrays. We'd have a good idea how we'd make launch vehicles. It's not basic science, it's technology, it's engineering. People are starting to look at microwave power transmission in terms of a market, including solar power satellites. A friend of mine, Buzz Aldrin, moonwalker, astronaut, he recently came out with a policy statement saying that we needed to have a strategic vision for enabling space-based human economic expansion and industrialization, incubating that, and investing specifically in space solar power. There was also an Abbey Lane Baker Institute report as to what NASA should be doing under the new administration. They also recommended that space solar power deserves an increased look. And they said that we should be heading towards demonstrations. Our sort of the equivalent of your Chamber of Commerce, our Chamber of Commerce has a subsection that's space enterprise. And they said that in a balanced portfolio, it should include the study of space solar power, that a number of the technology advancements strengthened the case for including it in the mix. And they noted that it could create new economic opportunities for launch, space utilization, many spin-offs, that it might lead to significant improvements in solar cells that would have an effect both in space and on Earth, and that it might actually generate revenue before deployment of systems as a result of what might be built. So then think about the business sense, right? This is Ivan Becky. Some of you in the aerospace world may know who he is. He's wrote some fabulous books, including Advanced Space Systems, 2020, 2030, NASA scientist, incomparable mind. He took a look, and of course, I assume you guys can see, but this is a logarithmic scale, so every time 10 times what the previous one was. And he said, well, if I had inexpensive launch, where are the real markets? And I want you to notice that this is space solar power. That's public travel, various other things, but the fact is that this dwarfs every other potential market for aerospace. And of course, there's a lot of Indian expertise that could be brought to bear. People who have space system expertise, electronics expertise, fundamental research in the subsystems, and of course, interest in building. Typically, the first generation is going to have to be terrestrial, launched from terrestrial. But in the long run, there are a lot of really significant reasons why you'd rather take the materials from the moon or take the materials from an asteroid, because the energy cost of getting it there is so much lower. Then you've got to decide where you're going to manufacture it. Typically, people think about manufacturing the power generation and the satellite here on Earth. And there's almost no, I mean, if you want to make a mark for yourself in this world, in this area anyway, no one's thought about how you would produce an industrial process in space if I launched bulk materials and then wanted to use the high vacuum and the abundant energy to manufacture there. Similarly, very little work on the moon, only very low-grade photovoltaics using the lunar regolith. Then you've got to think about how you're going to get the satellite to where it needs to go. The typical one that I'll talk about is a two-stage-to-orbit system. The proponents in India typically are looking at the single-stage-to-orbit. There are ways that you can enhance either one with a magnetic lev, or you can try to launch directly, because if I'm not launching people, I can take 30-plus Gs. It's not a problem. And there are ideas about elevators and partial elevators and laser launch and microwave launch and nuclear thermal propulsion. Then you've got to decide where you want your orbit. Typically, people talk about putting it in GEO, where the satellite appears to be stationary over one area. But there are other designs that you can think about, particularly if you have multiple customers on the ground. And then you've got to think about how you're going to generate it. There's a great debate on which of these is really the best, and not a terribly good amount of clear-headed literature on how to do it. And then you've got to select your transmission choice. And there are a number of interesting. There are ideas about having a space relay network of power. There are typically the ideas revolve around about 2.4 or 5.8 gigahertz, about what your cell phones and your laptops use. And then there's also ideas for doing it in the visible or near IR spectrum. And then you've got to think about who your customer is, because base load is going to be more challenging than peak or niche customer, or perhaps even desalinization. So because you want your mass on orbit to be small, you want to have as little losses through the atmosphere as possible. So the below 10 gigahertz is attractive, and the near IR is also an attractive place where the atmosphere does not cost you too much as you beam through it. So a useful analogy is a hydroelectric dam. It's going to have very high capital costs. It's going to have a long payback, but there's no fossil fuel, totally renewable, and it's about a similar scale in terms of big numbers. The other thing is, and this is what I encourage you to think about as engineers, right? There was a time before any of these were built, when we'd only built maybe very small dams. And somebody was saying to themselves, you know, I think we can do it. I think we can dam a river that big. And I think we can get gigawatts of power out. And I'm sure there are many naysayers that said, holy cow, we don't know how to do pre-stressed concrete like that. No one's ever built anything of that size. No one's ever scaled up these turbines and generators. You know, the cost today of the concrete pours to do that is astronomical. We don't even know how to produce that much concrete. All those are comparable questions to where space solar is today. We know how to make photovoltaic cells. We know how to make transmitters. We know how to make space structures, but nobody's ever made anything that big before. And you can think of a reusable launch vehicle as very similar to an oil platform. It's very close in cost, actually. And this allows you to drill up and access energy. So I think that it's time that those concepts were linked, that people understand that this is actually an energy mining tool. It's not some fancy aerospace plane by itself. Now, if you look at, if I want to generate 1 unit of power, and I look over the entire life cycle of a space solar power system, people have done this study in Japan, the total cost of manufacture and launch over the entire lifestyle would produce about that much carbon dioxide. Coal, 60 times worse. So think about how significant that could be in terms of long-term climate stability. Now, how does the typical architecture work? There are some designs that don't use concentrators, but typically you have some kind of mirror that focuses it on some kind of energy production, whether it's solar dynamic, meaning rotating machinery, or as photovoltaics, of which there are different designs. Some are thin film, some are planar, some are concentrated PV. Then it gets converted, the energy gets converted to electricity, and then that gets converted typically to some type of electromagnetic radiation, typically microwaves. In the microwave scheme, you have a fairly huge multi-kilometer across receiver structure called a rectenna, because it receives and rectifies the current. It's a series of dipole antennas. It's mounted on a thin metal screen, typically. The literature says that it's very efficient in converting the energy, more efficient than we ever think that solar cells would be. And that matters because in land usage, this is like 80+% transparent to sunlight, so you could use the underneath of it for agricultural or pastoral purposes, or in the latest ideas, open or closed algae biodiesel farms. The other significant point that I want to make here is that this looks large, but it's really about the size of an airport. You know, we appropriate that much land for things like that all the time. But if I needed to produce this much power with photovoltaics, it's actually a lot less attractive. It would have to be much, much larger, probably on the order of perhaps 20 times larger, if I'm going for the base load power, which isn't necessarily the best use of solar energy. The other problem, or the other reason why this is attractive, besides the fact that I can produce much more energy per unit area, is that it's more benign to the ecosystem. The actual way that I know some of you are curious about the beam, right? So everybody's curious about the beam because they think, oh man, microwaves in space, weapon, it's going to fly off the side, fry cities. You know, fortunately, that's not the way it works. The actual way in which you decide the strength and the characteristic of the beam has to fit this fundamental characteristic. As an average over time, it has to put out more energy than the equivalent area of photovoltaics on the ground would. So you initially think, well, then it's got to be a way more powerful beam than sunlight. But that's actually not true because for two reasons. One of the reasons why this can actually be a beam far weaker than sunlight is that the conversion efficiency is much higher, and it's beaming 24 hours a day. So it can have a lower average power, but it fills up the bucket more than having a peak and then a valley in traditional solar. So you can actually get away with producing significantly more power by beaming in at a sixth the intensity of sunlight. And then the beam tapers as a Gaussian out, and the way it's actually focused is you have a pilot signal that tells all the sub-elements to focus here. if you have a lot of energy, you can think about ambitious things. You can think about water production. You can think about manufacturing green fuels. So the problem with fossil fuels or liquid hydrocarbons now isn't that they're fantastic for every possible application. There's nothing that has the handling, the temperature handling, the safety, the density. Hydrocarbons rock. The problem is that there's no closed carbon cycle. So if you can have plenty of energy coming in, then you can think about manufacturing hydrocarbons and then turning around and sucking the carbon dioxide back in a complete loop. All right. Again, beam direction and concentration. The other thing that's very important to realize is that this size of the receiver is really one of the largest economic drivers. This is one of the most mass-intensive parts of the satellite. So nobody's going to deliberately grow it larger than it needs to be. There's a relationship between the transmitter and the receiver that's fixed. Doesn't even determine how much power it goes across. It's a matter of the physics of power beaming. So this is going to be tuned to this particular area. It's also selected to have a power that's significantly below, about twice below what people think might have an effect on the ionosphere. It's non-ionizing radiation, meaning that it's not going to strip off electrons in your cells. It's not bad like UV sunlight. If you walked under it, you would feel warm. You wouldn't walk under it because it's fenced off around the sides. And at the edge of the facility, it's actually lower than the amount of energy you get when you hold your cell phone to your head, but it's approximately the same as the safety regulations for standing next to your microwave. So, when we first started looking at this again, the question that we got from everyone, well, what's changed since the last time you looked at it? Well, lots changed technology-wise. Lots changed in the strategic climate. When it was last looked at, the fears about fossil fuel supply weren't really within a generation, and the concern about climate change was not as significant. But technology-wise, we've got 40+% efficient solar cells in the lab now. A lot of interesting work on materials and beaming technology, robotics, construction, gossamer structures. Tremendous work that's happened and is happening. So if you look at where we were compared to the last time it was seriously looked at, efficiency of solar cells were about 10%. Now we're 40. Many people think it will only be a few short years till we're at 50. I heard a report from one friend of mine who just retired from NASA that he thinks he's achieved in the laboratory 64% efficient photovoltaics at one sun. Pretty amazing. All right, wireless power transmission. We were at less than 20%, so people were talking about gyrotons and klystrons typically. Now the efficiency people are thinking about in these wavelengths for this specific application appears like it's going in a very attractive direction. The power management was extreme in the old non-modular designs. You had to carry across amazing 50,000 volts across very small gimbals. Now the new systems are less than 1,000 volts. The space launch requirements for the way people were thinking about it architecturally then required unbelievably large reusable launch vehicles. Now we think we could do it with very achievable 25-ton launchers. Space robotics, it was so immature you could not even think about not using astronauts for construction. Now a number of demonstrations make you think that perhaps you could do an awful lot via autonomous and telepresence. And of course the assembly, you reduce the manpower, you reduce the overall cost. So as I said, a lot of people also have the following question in their minds. It's a smart question. Man, if you are beaming in these 50 to 100 terawatts into the biosphere, aren't you adding a lot of heat? Don't you need to worry about global warming? The answers to that is manyfold, but they're all no. First of all, if you total up that entire energy expenditure that you'd need for humanity, the reality is that it's within the momentary fluctuations of the solar constant. So it's not significant on that level. The second thing is that the heat that you would add is dwarfed by the heat that you don't keep by removing the source of carbon dioxide. So it's extremely mass effective. In fact, you'll see these bizarre, wild ideas about putting a sunshade at the Earth-Sun L1 point to block out part of the solar constant. Well, that would be way, way more mass and not actually remove the carbon. So this is a much more useful way to get to it. But the other thing at the very basic level, right, is it's not how much energy you put in, it's how much energy you keep in the biosphere through inefficiency at the generating source. Of course, at the demand side, it's all going to be the same. It's all the same waste heat. But here you've got 15% 15% rejection of heat via a rectenna versus, even if you had 50% efficient photovoltaics, you'd be rejecting 50% of your waste heat to the biosphere. So this appears much more benign. The CO2 emissions, again, about a 60th what coal is, fairly, just slightly lower than nuclear, very comparable. Another question I had, I'm sure all of you guys have, is, well, you're going to spend so much energy launching that on a rocket, making it. How can you ever get the energy payback? Well, people have done the calculations, and the entire structure, the entire endeavor appears to pay off in about 2 years, which is very comparable to ground photovoltaics. And of course, the nice thing is rectennas don't require water cooling, so that things like nuclear or other fossil fuel plants that require huge amounts of water, that's not a consideration. And as I already spent some length of time talking about, the land usage is much more benign because you can use it for other things underneath it, and it produces much more energy per unit area. Here are some examples of what previous satellite designs have looked at when people have considered it. This was the first reference design. It was a planar solar array with a single transmitter that was gimbaled, and it was actually mechanically pointed. This is a later design with with an electronically steered array. This is the photovoltaics here, and here these are like mylar focusers, and that would be the high concentrating. Here are a couple different ideas. This might be either photovoltaic in this case, or you might think about modules like this for solar thermal. Many people who think solar thermal is the better way to go because they think the efficiency is ready now, and you could get the rotating machinery mass produced. And they point that the eventual direction for photovoltaics is assumed, but the Brayton-Rankine cycle is here today. This is another very different one. It's a solar disk. It's a thin film array that's gyro-stabilized. This is the more typical, more modern designs that are being pursued in Europe. Europe does have a program in space solar power. It's very small through their ESA. And then this is the PSU-1. It was a company that was trying to get it started. Ultimately hasn't been successful yet in finding funding. This is the modern one. I don't know if you were here and saw any of the video in the beginning. This is sort of the system. The way this works is this is gravity gradient stabilized, because the important thing in a space solar power satellite and the very difficult aerospace problem is that the transmitter always has to point at the ground, but the collectors always have to point at the sun. So if you imagine the way this works, if this was the equator here, these would pivot around to face the sun. This would hang down, gravity gradient stabilized. And the way this works is you have an initial, and this is like 7 kilometers across, just to give you a sense of scale. And it might be somewhere between, say, 15 and 50,000 metric tons. And you think that today's ISS is about, I think, 230 metric tons. And it puts out 120 kilowatts. This is putting out about 5 gigawatts. But in any case, in this design, you have a series of individual spacecraft, actually, that autonomously assemble themselves, hexagonal spacecraft. On the top, they have photovoltaics. On the bottom, they have essentially an electronically steered radar array. And then, of course, the interesting problem for aerospace guys is the waste heat rejection, which is radically different in how you think about it with thin film or planar or concentrator PV. And no one has really done very good trade studies, in my opinion, that show, if I include the total structural mass and the heat radiator mass for a concentrator, how does that trade against thin film? Because here's the other thing that is really important, right? The metric that matters in a space solar power satellite is not efficiency. It's specific power. It's the energy you get per unit mass, because the primary driver of economics is the cost to install. So I have to pay for every pound I launch, so the lighter a satellite is, the less I have to install, and the lower launch cost is, the cheaper it is to lift anything to space. Wireless power transmission does have a nice long history. This is the Goldstone test that Raytheon did at the NASA JPL facility. It's all on YouTube. And I actually have a copy of the video on a DVD if anyone's interested in seeing it. This is, I think, one of the mentalities that I would hope to, again, infect your mind with. If you have a closed world ideology, if you think that the world is one closed system and we can't go beyond it for our needs, then it drives you to incredibly negative thoughts about what you have to do, draconian measures to control society, to put down consumer culture, to put down people, to limit social mobility. If you realize that all the wealth in the universe is out there, it's not down here. The scarcity mindset comes from looking at our feet instead of looking up. There's unbelievable resources up here on the moon and asteroids, in power. And that's the future of mankind. It's out there, it's not here. If we stay here, we will collapse, because a closed system, thermodynamically, just you have to exchange matter and energy with your surrounding environment. So we have to be very careful that we don't imprison ourselves in Earth because we don't take care of the commons, because we don't know who ought to own this concept, because we're thinking somebody else should, and maybe we'll wait, and maybe we can cheat or get something else. And then we have to be aware of this sort of crabs in the barrel where we don't want somebody else to get ahead and lift the rest of us out. So when I think about what are the forces that drive potential Indo-US cooperation on this idea, these are sort of the macro forces that I think are taking place. We all have a common security interest, global stability interest in development and new wealth. We have a common interest in climate security, in stemming in the long term. I mean, ultimately, is it really acceptable to let Mother Nature determine our climate? I don't think so. I think in the long run, we have to take care of our own garden. And so we have to look to the different types of platforms and security that will get us to a point where we are not so much at the vagaries of nature. Then there's energy security. We share a common problem there, and we share this need in global stability. Overall, we have very common values, values of inclusion and plurality and democracy. We both would like to see a much greater wealth in the world. And there's an increasing strategic outlook about what is a safe world that we all want to be a part of. Of course, there are obvious limitations. There always are. Protectionism, national competitiveness, different proliferation types of things. But as engineers, we have to think about how we can make the forces unbalanced in favor of movement. So on that note, here are some of the things that I'm exploring. There are three major dialogues that our two countries have. We have the Civil Space Joint Working Group, we have the Energy Dialogue, we have the Defense Technical Group, and then we have two smaller ones, the High Tech Cooperation Group and the Aviation Cooperation Program. And then we have certain civil groups that certainly could feed or add to this. You have your professional societies, you have your business interests, you have your joint business interests, you have things like the Indo-US Science and Technology Forum, which is an outstanding place to engage. And I think I already said we have this Aviation Cooperation Program. So what do I think we don't have right now? Well, frankly, I don't have enough, there's not enough of me. If you guys think this is an exciting concept, boy, I sure could use you guys in the ranks. There isn't a critical mass of advocates. We're very small. There is no academic center of excellence. If you're a high school student, you read about this idea, you hear Dr. Kalam's lecture, where do you go? There's not a university in the world that you can go that has any program in space solar power. And there is no coordinated push to put it on the strategic partnership agenda, even though it crosses all of those. I mean, something like this, it is civil space, it is energy, it has certainly dual-use capabilities that would need to be discussed here. It is obviously high-tech. There is an aviation component. It's lots of business and lots to the professional societies. But there again is the tragedy of the commons. It belongs to everyone in general, so it belongs to no one specifically. So anyway, that concludes my basic talk. If there are questions, I think I do have some backup slides. But if you want to know more, you just Google NSS Space Solar Power Library. Everything that we could ever find that's been published is there. What I would say is that if you know of any documents that any Indian has ever done, please scan them and post them. Let me know, shoot an email to me, because we want to make sure that that entire library of technical work is available to everyone. And so with that, at the moment, I will, pending further questions, I'll quit this briefing, and I'll let you guys ask what's on your mind. And that may or may not drive me to show you some more slides. Please, sir, go ahead.
The first question that crossed my mind after your video is, I read in the newspaper yesterday that North Korea had launched an aggressive military rocket sometime back. And doesn't this pose a major security risk, as in it's a huge investment, but it can be taken down by one missile. So I'm looking at it from the security.
I spent a lot of time looking at that, actually. And here's my basic thought to start off with. A comparable system on the ground is way more vulnerable. I can get a missile, I can get an individual with a backpack, sever transmission lines, hit something. So the cost investiture to go to space to do it is a lot higher. I'm no less vulnerable, or I'm no more vulnerable in space than I am for the nuclear plant on the ground. The other thing is, I would not think that the terminus of this idea would be that one nation would have them and others wouldn't. I think everyone would be invested in a collective regime, which I think is a very positive vision for the humanity in space, that something like this could not be done without significant global governance. I don't mean global governance in the sense of governing the globe. I mean, the globe would have to be very much participating in the governance of that region of space where it's being mined. I think that, that just like any other energy source that we have security for, you would probably expect some kind of international security regime to protect against that particular eventuality. And I don't think in this world it would be that difficult to protect against that. And then, you know, there are honestly very few states that currently have that capability. There might be, of course, in this world many more, but I think that you know, the collective nature of this would have a lot of disincentives. But on the other hand, the fact that it has high costs is also sort of self-deterring. So I think that's also sort of positive for world stability. These are my own thoughts.
In what form do you plan to utilize the energy once it is transferred to Earth?
So there are, typically it's turned into DC, and then perhaps AC, and then moved over as, you know, very, very well-conditioned, very reliable electricity. Now that's not necessarily the only way, because let's say that you are, you know, this is dispatchable electricity, so the grid won't always need as much as you can provide. So when it's not doing that, you probably might want to channel it into the production of hydrogen for storage. You might want to use it to do the kind of LED lights in your electronics center, and you might want to be growing massive amounts of algae biodiesel. You know, there are so many ways in which you could use the excess energy, but the basic energy you're going to use as conditioned dispatchable electrical power.
microwave transmission system, first of all, how efficient it is, and then won't it be affected by the atmosphere below, and how safe is it? Will it pose any threat to the people below? And how many receiving stations do we need down on the earth to receive it? I mean, it's revolving around the planet, right?
Well, the answer to that is yes and no. If it's in geo, it is revolving around the planet, but it's revolving around at the same rate that the Earth turns. So if you were to look up, it would appear to never move, just like our communication satellites. Communication satellites have to have tremendous amounts of spacing in between because their transmitter is so small, they squirt their power everywhere. As you grow the transmitter to 0.6 to a kilometer in size, you're able to keep the power very focused so you can have the satellites at much closer densities than you do with communication satellites. So, you know, there are different ideas that you might be able to have one thing power share across different receivers. But the answer typically is that you sort of have in mind one satellite, one receiver. The estimates for what it would take to make up the deficit in world energy, if you read Mike Sneed's paper, are on the order of 1,200 such satellites. That's how huge our energy needs are, even just 60% of it. So I mean, for the United States today and for where India will be fully developed at the gold standard, you would need about 200 just for India. And if you think that's big, just realize what you're doing to your environment with coal and with nuclear. That also, in fact, coal takes up more area when you include what has to be done in terms of mining than a rectangle like this. Oh, hold on, before you asked about efficiency, right? So the estimates for efficiency span from about, from DC to DC, right? From the point that the photovoltaic ends and supplies power to the transmitter to what you get into the grid. The estimates span from about 25% end-to-end efficiency to as high as 60% end-to-end efficiency. Let me see if I can find an example here. Now again, I wouldn't take anyone's word for it. I think this is something that, I mean, obviously it's never been actually done before, so it requires significant consideration. But for instance, people who have published numbers, this is one efficiency chain that some would think is overly optimistic. But essentially, this is using a thin film application where it's only like 16% efficient, I think, or maybe it's not thin film, but it's about 16% efficient photovoltaic. So you're rejecting about 84% of that to space. Then you go from 9.4 to 1.45 into this. This is inefficient. You reject about another 21% to space. Then you lose about only 2% going through the atmosphere, and then you lose about 15% when you actually come onto the antenna. So that would be an efficiency chain that is aggressive, and some think too optimistic. The one by the efficiency chain that I've seen from a very respected space engineer who recently looked at it, he said it was about 33% end-to-end. So whatever you needed on the ground, you'd need to multiply how much was going into it by 3.
And the distribution losses from the source of generation to the end consumer, they are about 20%. Here, if the solar panels on ground, they can be directly installed at the consumer itself. Right? In India, where the population is so much dispersed, it is more efficient to have a ground-based power source than somewhere out there.
So for small applications, you're absolutely right. Particularly if you're in farming, for instance, and you only need power during the day, or you're only thinking about it in terms of air conditioning, or you're only using it for the day, that's true. Now, the thing that you have to keep in mind as an engineer, right, is that whatever the efficiency that you see multiplied up here, you also have to keep in mind that you have very, very difficult, if you want to be going for reliable power, not just, oh, the sun's on, so I've got some light, or I can make my pump work. No argument. I wouldn't say build solar power satellites for rural applications. But keep in mind, 2050, you're going to have 60% of your population, more than 600,000 in cities. So the other thing that you have to consider about that is that any ground photovoltaic system has got whatever the efficiency multiplier is for the cell itself. Then it's going to have a 0.2 to 0.22 to 0.25 maybe duty cycle that you have to apply. And then that multiplier has to be applied to a round-trip storage efficiency of what, maybe 45% in and out when you talk about large scale. And if you really look at that, I mean, it's extreme. And these slides are not really mature enough for me to talk to well. But if you look at a large-scale solar power system, this is, let me see if I can find it here. All right. So again, don't take these numbers for it. This is me basically in a scratch pad looking for how to communicate stuff better. So in this system, if I were to compare how much I get in terms of gigawatt hours per year, per unit land, right, I'm doing, depending on what the actual, where I'm at in the world. And that's the other thing, right? This system is appropriate anywhere in the world, not just in southern India. But I'm getting 1.6 to nearly 5 times at that low power beaming. Keep in mind, there are people who think that environment, personal safety, animal safety, no problem with doubling the amount of beam density here. But 1.6 to 4.7 times the annual output versus a PV array. And then if you look at what the PV that would be required to be manufactured, you'd need this much PV if you put it in space. If you were to put it here, this is without storage, you'd need it to be 1.7 to 5 times as large there. And let me see what else I got to show you. I already showed you that slide, but this is sort of how the whole thing would go. If you need this much on the ground, 1, and you include, what do I really need in terms of the day-night cycle, I have to have that much more than what I think I want on my nameplate power. Then, if I take into consideration my storage in winter, it goes up that much. And then when I think about, well, what if I have to be able to provide power when it's overcast for a few days, it really goes up. Versus in space, I start off with a smaller cell than this because I'm already getting, at peak power, I need less. And then with transmission losses, I need some multiplier of this. This assumes 66%, but if it were 33, it would be like that compared to this. And then I also have to rationally add what is the land area that I would need in order to get the rectenna on the ground. And of course, it's not universally scaling because space solar, at least in microwave, you have to go big because the diameter of the transmitter and the receiver are independent of the power beam between them. So it doesn't make sense to build something that's a kilometer across in space if you're only building a few megawatts, right? If the same area is going to get you gigawatts, it makes sense as a concept to go big. There's another slide. Okay, I wanted to address this. So this is a friend of mine did this up for Austin. This is what it looks like in terms of summer and winter. Austin's sort of like down here. It's pretty good weather. If I need a 1 gigawatt for 24 hours, right, I have to count how many hours of effective full sun. I need 1 gigawatt for 24 hours, not just 1 gigawatt at peak, right? So, but 1 gigawatt would produce only 4 gigawatts, so that leaves 20 that need to be supplied some other way. So in order to make it big enough to capture everything that I need for 24 hours, I have to be able to do it in just 4 hours of winter sun. So that means that, and I have to calculate what's lost and retrieved from storage. So, you need to have essentially an 8.8 gigawatt collector that generates 32.5 gigawatt hours and only 4 hours of effective sunlight in wintertime. This is how it's used. 4 gigawatt are used directly. 31 hours are stored. and then 11.2 are lost. This assumes the best for large scale right now, which is pumped water storage. So a collector this size would be 350 square kilometers. It would weigh 3.5 billion tons, cost $37 billion. It would meet a massive pump generating storage facility with 2 reservoirs, which would likely cost on the order of $12 billion. And it has no reserve to cover totally cloudy days. So imagine that, is that the future that you want for your country looking like that? If you try to scale that up, right, your 2100 needs are going to be remarkably close to ours, so 300 baseload gigawatts. You'd need to be able to provide, for us that would be 1/3, pump storage would be 1/3 the area of Lake Erie. I mean, just think about that. And it would cost somewhere in the order of $10 trillion. So anyway, and that's sort of looking at what it would take in terms of water usage to be able to store it in pump storage. And that's what we call baseload. Baseload is what always is needed, regardless of the peak in the day or the non-peak in the day.
I have one question regarding the microwave scheme that you had mentioned.
Okay.
You said that the scheme is, the atmosphere is transparent to the microwaves. But if I'm not wrong, doesn't water have a absorption peak in the microwave region?
Believe it or not, in order to get your microwave oven to work, you have to bounce it back many, many, many times and increase the coupling. So the frequencies that are chosen are the ones that are going to have the least stoppage that's been measured in the atmosphere. Is there? Yes, there is, but you saw it's about 2% losses through the atmosphere.
Based on how much the governments are exerted, how much the corporates are exerted, what do you think will be the percentage of contribution from this idea by 2030?
The percentage of energy being supplied by this in 2030? Holy cow, that's what I need you to answer. Because right now, keep in mind that we think, talking to the people who I think are the best informed right now, that it would take about 10 years to get to a truly relevant demonstrator. And when I say truly relevant, I mean it's using the frequencies, it's using the components, it's doing it over the same distance in the native environment that it would be used, and it's beaming at least as significant, and so that it can be directly upscaled, right? The thought is that that will take about 10 years and about $10 billion to get there. That $10 billion isn't really that much at $1 billion a year for something that could change the world. But let's say that you did such a good job that in the 12th year you were ready to launch. Then, of course, you have to look at the launch infrastructure and how you think you want to do that. And so let me, I actually do have a chart. It's not my chart. Point to the fact that once you get over a certain number of flights a year, which we do about 10 times going to space a year, but once you get over 50, there's a significant decrease. There are things that you can do in terms of lowering the amount of touch labor that are required. And then once you get into 100 to 500 flights a year, it really comes down in price that you can think about it being less than $100 per pound or $200 per kilogram. There's no fundamental physical limit to that from what I understand. Now, in terms of the satellite costs, right? Satellite costs today are just astronomical. But as you produce more units, right, and in this case you'd be producing them even a factor of 100 above the cost of consumer electronics, and keep in mind the scale of this would be comparable, you can get to where you need to go. But mass is reducing, which is a good thing. And then as you look at the learning curve, the actual cost per unit of the learning curve, this is Iridium and how much cheaper it was to manufacture, whatever it is, 36 satellites versus 1. That greatly reduces the cost. There's a lot of interesting work in thermal radiators. And then if you look at what have been specific power estimates, these are what people have thought you could do over the entire spectrum for watts per kilogram. Now, how could you get to low-cost launch? The chart I showed you before assumes a very standard, what we call technological readiness 6 level of technology, which is a two-stage to orbit system. Even that is projected to be able to get down to the cost you want. If you're able to go to an air-breathing platform, which is much more challenging, then those costs could conceivably be even lower. There's another really out-of-the-box interesting idea called a radially segmented launch vehicle, where essentially every piece of this rocket is manufactured in automotive manners and kludged together. The mass fraction is terrible, but the economics are really attractive because you're making the same thing many times and you're building it differently than aerospace does. So these are some ideas that are bouncing around in the heads of your aero departments and your Department of Space. This is your two-stage to orbit ISRO system that's being contemplated. This is Avatar hyperplane, many different pictures of what the design might look like. Now there are interesting hybrid approaches that also make it more attractive. So one of them is that you don't necessarily have to have the energy to get all the way to orbit. You just have to be able to get to a height at which you can offload what you have onto a tether. And you can have the tether up there, and the way that that works is, think of it like an accumulator. Once it's up here, the problem is, how do you boost this whole mass? Well, if you're not immediately having to worry about drag and coming back down, then you can use much higher efficiency electrical thrusters. And so what essentially you do is you pop up, you drop off what you need at the bottom of the tether, and then you come back down. And that is thought in more recent studies to be achievable with materials today. Here's another example of what's called the skyhook. Then you can reduce some of your cost with a 0th stage by launching in a maglev system. You might be able to take off only with fuel and refuel oxidizer. You might have an air-breathing first stage and then have a second stage. Then there are farther out ideas that aren't appropriate for human launch because of the high Gs they experience, but are interesting to contemplate for high mass flows. And these are, you have the laser launch idea, which is getting more mature all the time. This would be very small. You'd probably be launching only, say, 100 kilograms, 200 kilograms at a time. And then you'd need to think about, how do I manufacture on orbit? So I'd be launching raw silicon, raw gallium, whatever up there, and then I'd have to think about, how do I manufacture in orbit? Similar thing with this. This is actually a microwave thermal concept. Basically, it's a single heat exchanger, pure hydrogen. Then you've got the maglifter concept, which is basically a straight maglev, just like a train, and it takes a certain amount of power and zaps it off at very high rates. Interesting problems with all these. They're on the horizon. This is a microwave ion drive by Lake Mirabo at RPI, who also has some very interesting ideas about a space solar power satellite that stores its energy in superconducting electromagnetic self-inflating rings and then burst beams its power down at, when it's over the orbit. Of course, that has very different environmental impact that would have to be assessed. Then there are other longer contenders, right? I would much rather be able to use, I can manufacture like 99% of the mass of a solar power satellite from the moon, and I don't need fuel at all if I launch it electromagnetically, and I don't have to worry about aero loads. I could build a much weaker structure, lower mass, and launch it from the moon. Or if I didn't want to go this way, I could produce lunar oxygen from the regolith and use that as my propellant source, asteroidal resources. So when people looked at, solar power satellite as the killer app, that no alternative was really found to the manufacture of solar plants as a major commercial enterprise. This is back when they were thinking about very ambitious space colonies like this, and they were plotting, what would be the wealth generated. But so here's an idea of, what you might be able to get to. So this is what John Mankins thought was realistic. He thought you could get to a pilot plant about 2020. He thought by 2040, without significant upscaling, you'd be at 10 to 20, and then you'd be at a position to keep launching from terrestrial and to start using asteroidal resources, lunar resources. So, and why would you want to do that? Well, here's the fundamental reason. As I said, there's a study on the NSSO website I showed. It takes about 8% the energy to get from this low gravity well to where you need it versus, dragging it way up this steep gravity well. And so, theoretically, if there was some scaling, it might be a 50th the cost. And you can build, all this material is up there, so you'd only need about, you'd only need to take about 1% of vitamins from the earth to make sure that you could manufacture what you'd need to manufacture. And so when they looked at the total mass flow of what was needed to construct, this is an old NASA study, but this is, one of them is the mass driver and the other is the lunar oxygen example, but this is the Earth baseline and total Earth launched payload. You'd have to launch a lot less from Earth. And then this is sort of what the architecture looked like. All this is on the web page. This one was a mass driver with a mass catcher, and then it would be assembled in space and then moved from there. This one is using the lunar transport with the oxygen on board. And there's a lot of iron and titanium, and there's thought to be significant rare earths, platinum group metals. And the reason why is if you look at the moon, it's got tons of craters. All of our platinum group metals, all of our rare earths come from what are called astrobleams. They're asteroid strikes. Asteroids hit the Earth. The rest of our heavy metals are all in the center, because as the planet coalesced, the heaviest things move to the center. So the things that you get, the indium, the platinum, all the things that are important for solar cells and catalysts and that sort of thing, they're gifts of giant asteroid strikes in the past. Well, the moon has tons of craters, and they've done studies on what they think would be the actual vaporization and what might be there to be found and mined. It's very worthwhile, people think, looking for that sort of stuff. The United States is thinking about going to the moon. I don't think, unfortunately, we have this as part of our fundamental vision. The Chinese definitely do. Moon, crucial to the sustainable development of human beings on Earth. Whoever conquers the moon will benefit first. I think they've got the right idea. Russia's also got an idea. They're looking at helium-3, which I think is much farther out than space solar power. So, anyway, hopefully that answers your question in a roundabout way. But I mean, it's all scale, right? Let's say that you needed to replace everything that you needed to replace at 60. You'd need to be launching about 25 a year from your start. Really, you wouldn't do that. It'd be averaged. But if you look at that, I mean, it's like 5,000 launches per satellite, which is incredible to contemplate, right? I mean, that's 1,000 times more, factor of 1,000 more than we launch today. But if you look at it compared to a busy airport today, it's tiny. It's not even close to Chennai Airport in terms of how often things are coming and going, and it's nothing compared to the mass flows of a major seaport. So in the scale of what we're used to, oh my gosh. But on the scale of what human beings are capable of, it's tiny. And the other thing I would tell you is, let me see if I can find this particular slide here. All right, this is sort of an interesting piece of history. In a roughly comparable period, right, once people started seeing that there was value in oil, it grew over 100-fold in production in a very, in a 100-year time. Coal grew 300-fold and natural gas grew 800-fold. So, I mean, energy is so fundamental to all human activity that once we find it, once we prove that it can be done, everyone's going to be looking to do it. So, and once we do it, I'm sure we'll figure out way better ways to do it once we're there. I tell you what, if that's the end, do you have the video? Is it in here? Or is it over there? For those of you who came in late, I'm just going to show a very short 4-minute thing that we did because we recognize the tremendous need to draw individuals like yourself into math and science and engineering to ensure the long-term sustainability. And it does have sound, correct, or not? It's fine. Any other questions while he's throwing that in? So, I mean, our satellites now last amazingly long times. We've still got satellites from the Cold War era that are doing just fine. Some studies assume about 20 years on the conservative before significant refurbishment. Most studies look at about a 40-year return. And now that doesn't mean that there'd be no maintenance in the meantime. You'd, of course, be replacing, you've got to expect that you're going to have radiation degradation of your solar cells. You're going to have micrometeorite strikes. You're going to have debris that you're going to have to take care of from the massive amounts of construction that all have to be considered and factored in. So, but this was asked to a senior person at Aerospace Corporation. He said, look, based on the designs of current satellites, there's no reason to think that a lifespan of this is not achievable. Well, hold on. I never said that you'd build a strip, right? That's just where you would locate the satellites.
What I'm saying is for practical scales, we need huge areas up there.
That's right.
How practical would that be? A. And B, there's already a concern of a large amount of debris from satellites and other human stuff up there. So if we put up something like this and say 50 years, 100 years down the line, its lifetime, how do you plan to get back down?
So you don't actually get it back down. You move it to a higher orbit. I have seen an economic study that looked at it, and it's actually a very small percentage of total costs for the fuel to move it to a higher graveyard orbit. Regarding the debris, the problem that we have debris today is a purely technical problem. There are credible studies that basically say that you could have a single ground-based laser facility that would zap one side of a piece of debris, would flash heat it so that you have an off gas like a rocket. That would alter its circularity so that it's more elliptical. The lower side of the elliptical, it hits the atmosphere and so it burns up, right? So the study basically says that you could clean up all the debris at LEO in about 2 years. So I think that that's something that is inevitable that will happen. So in the long term, a regime like this that's that important, that's that many trillions of dollars, I don't think that that's a long-term problem. I think people would dredge the harbor. Would you hit the second one? Oh, actually, wait. Did you already hit it? Actually, that's fine, because it'll run into the next one. All right, so this is something we made for the kids, America's math and science classrooms, but hopefully you'll enjoy it as well. And I think it provides a nice visual introduction. You got no sound. IT. Any other questions while that's coming up? Anybody in the back? You guys have been so... Yes, sir. That's a great question, and I do have some slides on what real money is and what's available. Let me see if I can find that while they're working on this. Because that was my question, too. I was just like, is there enough money in the world to do something that's ambitious? All right, so here's one estimate that's pretty close to the ballpark of what people think. The fabrication, somewhere around, on the order of $5 billion. Antenna, maybe a little less than that. Launch components and transport itself, the cost of $2 billion. So the total cost of an individual system, $15 billion. And that's assuming a launch of about 220 per kilogram. So if you look at just Exxon, right? Exxon has a 360, this is an energy company, right? $360 billion revenue. They spend $36 billion on exploration. They spend $12 billion a year on R&D. So it's not out of the realm of numbers. If you look at the world GDP today, we're at $65 trillion. The estimates of what's going to be needed just to bring up the fossil fuel resources by what we need by 2030 is on the order of $17 trillion. And then, and if you work that out, that's somewhere on the order of almost $1 trillion a year. So that's pretty large. And then I've seen estimates that by 2020, the energy market in Asia alone is going to be over $1 trillion. A company like Boeing has $50 billion on cash and $3.25 trillion in back orders. And of course, there's huge amounts being proposed, larger than this number, for green energy and green jobs. And then, you know, what global warming people think that's going to cost is on the order of $20 trillion over 2 decades. So I don't think that these numbers are uncontemplatable for scaling it up. Any other questions? Anybody else in the back? Anybody else burning questions in their mind? You guys have been a great audience. Right.
So it avoids the problem of weather and seasons, etc. But
Mm-hmm.
it doesn't get to the day and night thing. I mean, like once it's following a fixed location on the Earth, obviously it is revolving around the Earth.
Ah, okay. So that's not true, and I'll explain why. The orbit of the Earth is inclined to the sun. So the only time that the satellite is in shade from the Earth's shadow, because it's far enough out, right? It's like this. The only time that it's in shadow is at the 2 equinoxes. And that's a very short period of time. So it's in the sunlight 99.7% of the time. So you can easily schedule around that once a year, you're not going to have power for an hour and a half. And by the way, that is the reason why people like GEO, because the satellite is collecting energy so much of the time. But that is not the only architecture that people have thought about. For instance, if you have one in equatorial Leo, and you have enough customers around the world, you can have a series of them that move, and of course that means that the cost to get it to the higher orbit is less. So that is a possibility. You don't want to have it too low where there's a lot of drag, but that's a possibility. A MEO constellation or a magic orbit where it spends a lot of time in the same part of the sky and then comes back around. Also things that have been contemplated. There's also another orbit called sun synchronous where let's say that you knew that your maximum power was at a particular time of the day or that you needed to augment, like let's say that you had a saltwater desalination plant and you knew that you needed to provide power at the back end, at the night. You could make the satellite sun synchronous so it came over that particular area at that time. So all these ideas are out there, and I highly encourage you guys to think about it for yourself. The last word has not been said on how you design and think about these things. All right, well, it doesn't look like that's going to strike up for us. But if you want to see the full version, I think they showed part of it earlier today, right? If you want to see the full version, it is available if you go to thefutureschannel.com and click on Living and Working in Space. Oh, there it is. Hold on, they finally got it working. So.
Space-based solar power.
Long-term strategic energy.
Space-based solar power.
Space-based solar power.
I currently serve as the Chief of Advanced Concepts at the National Security Space Office. I was asked to pick up the study on space-based solar power.
Space-based solar energy is an idea invented in the 1960s. Dating back to when O'Neill and Glaser were promoting this idea.
One solar power satellite could supply as much energy as 10 nuclear power plants.
It isn't restricted just to those
countries which have oil or coal or natural gas.
It's a life-changing, a game-changing type of capability.
A potential for changing the energy game hugely. We're talking about putting solar arrays into space that are square kilometers in size.
Collect the sun's raw, intense energy, which is much stronger in space than it is down here on Earth.
Large mirrors have to always point at the sun, but the transmitter has to always point at the Earth.
Collect that energy in space and actually beam it. Electricity into the electrical power grids that already exist.
The challenges that we face right now with regard to energy and the environment are so compelling.
Looking at the energy problem,
Where's that energy going to come from?
looking at climate change,
We're facing an environmental contamination problem because of our consumption of carbon-producing fuels.
The fuels that are running out.
increasing populations, dwindling resources,
The population is increasing, the energy sources are decreasing.
looking at national security, some of the potential causes of conflict, American competitiveness, American leadership in aerospace and energy. If we take the 100,000-foot view of this whole thing, it's very large.
It is so huge. It is an enormous engineering undertaking.
Just to give you a sense of scale, each of these little disks is about the size of a football field.
We want to actually get space solar power happening right now. There's going to be a need for certain demonstration.
Proofs of concept.
I'm a senior engineer here at the lab in the Naval Center for Space Technology. People come to the lab with concepts that need to be demonstrated.
Behind me is our thermal vacuum test chamber. We use this to simulate the vacuum of space. We're here in our radio frequency test facility. The blue pyramids on the walls help to absorb the radio frequency energy so that when we do a test, we don't have a lot of reflections.
One of our objectives is to develop appropriate robotic assembly techniques.
What an autonomous robot does is it actually thinks for itself.
Let's show that we can beam power from one location on the Earth to another. And this has already been done. This has been done 30 and 40 years ago.
A lot of us and a lot of younger people are wondering, what can I do to solve this problem?
It's going to be the new generation of students coming through the system now that are going to be the engineers, the designers, the builders of these systems.
I study aerospace engineering at the Massachusetts Institute of Technology.
Certainly it all starts with those science and engineering and math courses.
It could be 10 years into your career and something you learned in college is applicable and helps you understand someone else's job.
Diameter of the receiver, and that's the wavelength of the beam. The area, of course, is pi r squared.
Ever since high school, I was developing an interest in doing engineering.
Space will become familiar for us.
The economies of scale kick in, and it becomes cheaper.
Fleets of reusable spacecraft.
Innovative solutions.
This is just too important to the United States, its allies, and the world.
This is something that's going to require a national commitment.
I can't think of a more ambitious project that a young person could make a larger mark on than getting us towards solving a problem like this with our long-term energy crisis. All right, somebody, you had a question. By the way, this is the wireless power beaming demo, but go ahead with your question. Yeah, it's significant. I mean, but it's calculable. We know we have a lot of test data that indicates how quickly different solar cells degrade over time. And there are different strategies to get around that. One is reef manufacture or re-annealing. Another is programmed replacement as time goes on. But you do lose a significant amount of your generating potential over the entire life of the satellite. Does it aim at replacing? So, there's no program, keep in mind, right? There isn't one now. So I can't answer that question, right? This is a hopeful idea that's out there that I don't think is crazy to contemplate because of what we know and think we can do technology-wise. But, I mean, Japan's got 180 scientists working on two concepts, one in a solar pumped laser and another in traditional microwave. ESA's got a very small budget. The United States, frankly, we don't have any budget allocated to it now. I did the only significant work, and we spent $0. The study was free. We volunteered our time on the internet, had 200 of America's brightest minds volunteer their time because they were so passionate about it. But you know, but that's it. I mean, is this an idea that that we can afford to just ignore and have nobody looking at? I mean, that's generates my passion for it, is that there's just nobody else picking up the slack. And you know, frankly, you know, all of us that you saw in the video, you know, we came to it because, you know, our jobs forced us to look at the long-term picture, and we came at it from a security angle. But it's hugely unfortunate, frankly, that this idea is being carried by us. And we're just carrying the water, holding the candle till somebody takes it over. You know, it's highly unfortunate that the idea's rebirth, both here and in India, you know, is started from military people, because it's a civil project, and it ought to have advocates elsewhere. But you know, until I can find, you know, somebody who's willing to jump up and take over and wrestle me for it and say, "Doggone it, I want it," and I'm fine, you know. But you know, but right now, like I said, the cadre of us who think that this is one avenue to save the planet, you know, very small.
Thank you so much, sir, for that very entertaining talk. And space solar power seems to be a very profitable endeavor in the long run. I request Professor Ellis Ganesh to give you a memento. Thank you so much for being with us this evening and for patiently answering all those questions.
Thank you so much for having me. The privilege is all mine. Thank you. It's beautiful. Thank you again. And let me just remind you, whether it's space, solar power, or anything else, you guys are going to be the ones who solve the problem.